Hello, everybody, and welcome to the second lecture of week 11. So on Tuesday, we talked about Fermat primes, and today we're going to talk about Mersenne primes. So let me just recall that if we have a prime number L, then the corresponding Mersenne number is, which I write as M sub L, is 2 to the L minus 1. Okay, and then we asked the question, when is ML a prime number? So if you go back to week 7, we just talked about this a little bit. This was related to like this was related to perfect numbers. And we talked about the Lucas-Lehmer test, which gives us a simple way to check when ML is prime. And so in particular, the largest prime numbers we know are found by Mersenne primes using the Lucas-Lehmer test. Okay, so today we want to verify, or we want to sort of justify the Lucas-Lehmer test. Okay, and it's going to look a lot like how we justified the Penn test, but it's a little bit more complicated. So we're not actually going to give the Lucas-Lehmer test as we stated in week 7. Instead, we give the following equivalent version. So I'm going to look at the number alpha, which is 2 plus the square root of 3. In sort of z bracket square root of 3. So this is sort of this is the ring that's sort of all the combinations a plus b square root of 3, where a and b are both integers. So this is the kind of thing we've looked at a little bit before. And so then the statement is that ML is prime if and only if, when I take this element alpha and I raise it to the power 2 to the L minus 1, what I get is congruent to minus 1 mod ML, whereas here I'm working modulo ML, but it's sort of in this ring z square root of 3. Okay. So this is equivalent to the statement we gave of the Lucas-Lehmer test in week 7. And you'll see that when you look at exercise 3 on the worksheet. So you can sort of somehow rewrite this using only integers. But it's useful to, improving it, it's useful to state it this way. And in particular, when we say it this way, you can sort of see the relation with Pepin's test. So here we're raising this element alpha to the 2 to the L minus 1. This 2 to the L minus 1 sort of is closely related to this number, this Mersenne number ML. It's ML plus 1 over 2. Because ML plus 1, that's 2 to the L, and then you divide by 2, you just get 2 to the L minus 1. So this exponent is sort of closely related to this prime. Just like in Pepin's test, we saw that the Fermat number Fn was prime if and only if 3 to the Fn minus 1 over 2 was congruent to minus 1 mod Fn. So the point is Fn minus 1, that's a power of 2, and ML plus 1, that's a power of 2. So that's sort of that's the thing we're using in both of these. Okay, so just an example of how you apply this version of the Lucas-Lehmer test. Well, if I have, let me look at M3. So I take little l to be 3. So M3 is 7, 2 cubed minus 1. Then the number 2 to the L minus 1, so L is 3, so 2 to the L minus 1 is 2 squared, which is 4. So I should raise 2 plus square root of 3 to the 4th and check what I get mod 7. And so, well, I just take 2 plus square root of 3 squared, and I square that. So I'm computing this using successive squaring. If I square 2 plus square root of 3, I get 7 plus 4 square root of 3. But remember, I want to work mod 7. So this 7 becomes a 0, and I just get 4 square root of 3. And when I square that, I get 48. When I reduce mod 7, indeed, I get minus 1, because 48 is 7 times 7 minus 1. So I do get minus 1. And so this theorem tells you that 7 is a prime number. Okay, so maybe there are easier ways to check whether 7 is a prime number. But once you sort of start taking larger values of L, this becomes much quicker than sort of doing it by brute force, just trying dividing by numbers. Okay. So let me just remind you from Tuesday that the proof of Pepin's test for Fermat numbers used essentially the following facts. So the first one, and so the key thing that made everything work, was that we had this power of 2 floating around. Fn minus 1 is a power of 2. And then we were able to show that sort of if Fn was prime, then this 3 to the Fn minus 1 over 2 was equal to -1, just using quadratic reciprocity. Whereas on the other hand, if we just assume this was equal to -1, then we have this lemma, that used very strongly that this was a power of 2, to deduce that sort of 3 as an element, sort of 3 has sort of order 2 to the k in some group that was closely related. And so that was enough to deduce that Fn actually had to be prime. So sort of because the lemma says that sort of 3 to the 2 to the k minus 1 is equal to -1, then 3 has order 2 to the k. And then we use this sort of in the group FP cross for some p dividing Fn. Okay, and so we can't make the same type of argument for Mersenne primes using sort of this group FML cross, just because if I look at the order of this, like say ML is a prime, well, I get sort of the order of that group is just this ML minus 1, if ML is prime, which is just 2 to the L minus 2, and that's not a power of 2. So somehow there's not going to be a way I can sort of write down an element whose order is 2 to the L in here, because I mean somehow I don't like this is not what I want is I want this group, I want to have a group whose order is a power of 2, so I can sort of have an element whose order is a large power of 2 as well. But that doesn't work here, so I have to do something different. But I want to do something, like I want to employ basically the same argument. In particular, I want to be able to use this lemma to show that sort of when this thing is -1, that what I really get is prime. So I sort of need to sort of sort myself into a situation where I can sort of find something that has order a big power of 2. In this case, 2 to the L. I want to sort of find something that has order 2 to the L. Okay, and so the idea is that instead of using sort of FML cross, like so P is ML, sort of FP cross, I should instead sort of use a bigger field, FP squared. So I should sort of take, instead of a field with a prime number of elements, a field with the square of a prime number of elements. And the reason this is useful is because if I look at the like FP squared cross, well, this is just everything except 0. So this has p squared minus 1 elements. So here FP squared is some p is a prime and FP squared is a field with p squared elements. So there are p squared minus 1 units. And then p squared minus 1 factors as p minus 1 times p plus 1. And so if I take p to be a Mersenne prime, then sort of this p plus 1 now just becomes 2 to the L. And it's sort of this big power of 2 I want. And somehow the fact that p plus 1, this big power of 2 divides the order of this group, means that this group has sort of room in it to have an element where I can make this kind of argument. So I should be able to find some element of order 2 to the L inside of FP squared cross. And that's what we're going to use to imitate this Pepin argument by constructing an element of order 2 to the L in FP squared cross. Okay. And you'll see some related things on exercise 2 in the worksheet, which we started on Tuesday, and we're going to keep on working on Thursday. We'll sort of illuminate some of the things that are going on in the argument that's going to follow. Okay, so what does this have to do with the square root of 3 appearing in the theorem? Well, this is how we're going to construct, we're going to add a square root of 3 to sort of construct a field with p squared elements. So let me just say this statement. So here's the first claim. For a Mersenne prime ML, when L is, so we're always going to work with L greater than 2. 3 is not a square modulo ML. So I'll explain this in a second. But if you agree that 3 is not a square modulo ML, then I can look at this field FML and then add a square root of 3. So the elements of here is all the elements of the form a plus b squared root of 3, where a and b are in FL, F sub ML. And And square root of 3 is just sort of, you're creating a square root of 3. So square root of 3 squared is 3. And that's sort of enough to figure out what the addition and multiplication laws are. Just like sort of in class in this exercise 2, we were talking about FP bracket, FP adjoint I, sort of imitating the construction of the complex numbers, where we just added an element I, so I squared is equal to -1. Alternatively, you can think of this as being z squared of 3 mod ml, or you can think of it as sort of being f sub ml brackets x, the polynomial ring, the polynomials of coefficients in the finite field of ml elements, modulo the irreducible polynomial x squared minus 3. And sort of however you think of it, this is the field of order ml squared. So this sort of gives you a field whose size is the one we want to serve. It's not the size of the Mersenne prime, it's the square of the Mersenne prime. Okay, and so the reason this is a field is precisely because 3 is not a square modulo ml. So for example, if you look at like this way of thinking about it, fml brackets x mod x squared minus 3, saying 3 is not a square modulo ml is exactly saying x squared minus 3 doesn't have a root in this field. So this is, you're modding up by an irreducible polynomial, and what you get is a field. Okay, so that's sort of how the square root of 3 shows up. It shows up because this is sort of how we construct a field with p squared elements, or ml squared elements. Okay, so let me sort of justify this claim, though, that 3 is not a square modulo ml. Well, it sort of follows from quadratic reciprocity once we have 2 facts. First, ml is congruent to 3 mod 4. This is because ml is equal to 2 to the l minus 1, and 4 divides 2 to the l, because l is greater than 2. Okay, so this is equal to minus 1 mod 4, which is 3. In fact, this is also true sort of mod 8, which we'll use later. I'll come back to that. Similarly, like ml is 2 to the l minus 1. If I'm starting computing mod 3, I can write 2 to the l minus 1 is sort of 2 to the, so L is odd, so I can write this as 2 to the L minus 1 over 2 squared times 2 minus 1. Now, any square of sort of, any square mod 3 of something non-zero mod 3 is 1. So this is just equal to 2 minus 1, which is equivalent to 1 mod 3. So I have ML is equivalent to 3 mod 4 and 1 mod 3. So this is true for any Mersenne number, not just primes. But in particular, if it's a Mersenne prime, then I can use quadratic reciprocity now, which tells me sort of the Legendre symbol of 3 over ML is minus the Legendre symbol of ML over 3, because both ML and 3 are congruent to 3 mod 4. But the Legendre symbol of ML over 3 is 1, because ML is congruent to 1 mod 3, so ML is a square mod 3. And so this gives me a minus 1 total. So 3 is not, so the Legendre symbol of 3 over ML is minus 1, and 3 is not a square modulo ML, which is exactly what I claimed. Okay, good. So this gives us where we're going to work. This gives us sort of this field with ML squared elements when ML is prime. We're going to need a computation. So let's just sort of work for now, forget about P being a Mersenne prime. I just want to do a general computation, FP square root of 3, where I'm assuming that this is a field, i.e. that 3 is not a square modulo P. So in particular, this applies for P. This will apply for P in a Mersenne prime. So if I look at A plus B squared root of 3 to the P, then just like in the lecture on quadratic reciprocity, this is just A to the P plus B squared root of 3 to the P. Well, A to the P is just A because A is in FP. Then this is B to the P times square root of 3 to the P. So this is A plus, so B to the P is just B. And then square root of 3 to the p is, I can write this as sort of 3 to the p minus 1 over 2 times square root of 3. Okay, so that's just because square root of 3 to the p is square root of 3 to the p minus 1 times square root of 3, which is square root of 3 squared to the p minus 1 over 2 times square root of 3. So square root of 3 squared is just 3. Okay, and then that's just a plus b times, well, 3 to the p minus 1 over 2 is the Legendre symbol of 3 over p. And that, in the end, gives me just minus 1. So this is a minus b square root of 3. So sort of this interesting thing where this raising to the p power that we saw was a very useful thing to do when we were talking about quadratic reciprocity. When I sort of apply it to something like a plus b squared root of 3, it just gives me sort of something that looks like this conjugation. So a plus b squared root of 3 goes to a minus b squared root of 3. Sort of, this is sort of all happening sort of modulo p. But this is sort of the kind of operation we saw like when we were talking about the norm in like z squared root of 3 or z squared root of d. This is quite useful. In particular, if we apply it to the specific element 2 plus square root of 3, we get this fun computation. So if I look at 2 plus square root of 3 now to the p plus 1, I can separate that out as 2 plus square root of 3 times 2 minus square root of 3 to the p. So times 2 plus square root of 3 to the p. I'm just sort of separating out, just factoring out one copy of 2 plus square root of 3. But then using the above, this is 2 plus square root of 3 times 2 minus square root of 3. And now I just expand this out and I get 4 minus 3, which is 1. Okay. So this is really great. I mean, this is the kind of thing this is exactly what we needed. So this is sort of mod p. Because remember, this is the element, this 2 plus square root of 3, this is the element that was appearing in this statement of the theorem. And I'm checking that when I raise it to sort of the p plus first, so in this case, it would be like if p was ml, then the p plus first would be 2 to the l. So when I raise it to 2 to the l, I'm getting 1. And so that means sort of when I raise it to 2 to the l minus 1, I'm going to get a square root of 1, which is either 1 or minus 1. So I'm sort of halfway to sort of showing this is true. Okay, and so sort of building on that, we're going to now justify this main theorem that I just scrolled up to. So let's start sort of one direction. So first, let me suppose that p, so I'm going to take this ml, but I'm just going to write it as p for shorthand. Let me suppose this is prime. As I just said, if I take 2 plus square root of 3 to the p plus 1 over 2, then this is going to be plus or minus 1. And the reason is because 2 plus by the above two plus square root of 3 to the p plus 1 is equal to 1. So, but that's just 2 plus square root of 3 to p plus 1 over 2 squared. So this thing is something whose square is 1, but I'm sort of working in this field. So if I have something in a field whose square is 1, then that thing has to be 1 or minus 1. So, okay, so I get that this thing I'm trying to show is minus 1. I get that at least that's plus, like it's either positive 1 or minus 1. So I just have to rule out. I have to rule out the possibility that it could be equal to 1. Okay, so let me sort of roughly explain the argument for that. So suppose that it was equal to 1. Well, the only way that can happen is that if I sort of take a discrete logarithm So here, this is a discrete log for fp square root of 3. So I just have to fix some primitive p squared minus 1 root of unity and I get the discrete logarithm function I. So some of the only way that this can be equal to 1 is if this discrete logarithm is a multiple of 2 times p minus 1. So this discrete logarithm, this sort of lives in z mod p squared plus 1. Z mod p squared minus 1z. But p squared minus 1 is equal to sort of p plus 1 over 2 times 2 times p minus 1. So this is a factorization into 2 integers. So if I have something, so this equation, when I sort of apply the discrete logarithm, says that sort of p plus 1 over 2 times this is equal to 0. But that means sort of p plus 1 over 2 times this is a multiple of p squared minus 1. The only way that can happen is sort of if this thing I'm starting with is a multiple of 2p minus 1. Okay, so this discrete logarithm is a multiple of 2p minus 1. But if you think about what that means, well, that means that I can write it as a multiple. I can sort of write 2 plus square root of 3 as a square of some element. Yeah, I can write 2 plus square root of 3 as the square of some element that itself satisfies sort of whose p plus first power is equal to 1 mod p. So this is a little bit to untangle, but it follows from just working with the discrete logarithm. So this is the kind of thing we've done, like when we were talking about the Penn's test, which is a little bit more complicated. But somehow say like the fact that you're sort of a multiple, the discrete log is a multiple of 2 tells you it's a square. But sort of since it's a multiple of 2 times p minus 1, you could sort of write it as a multiple of that and then sort of, so let me just write this down. I mean, I of 2 plus square root of 3 is equal to 2p minus 1 times k. So if I sort of take g to the k times p minus 1 squared, so g is my primitive root, I will just get 2 plus square root of 3. So that gives me sort of a square root of this. But g to the k p minus 1 to the p plus 1 is going to be 1, because somehow this p minus 1 times this p plus 1 is giving me p squared minus 1. Okay, so sort of somehow this a plus b squared of 3 is this g to the k times p minus 1. Okay, but so yeah, I mean, the best thing to do is just sort of sort this out for yourself and write this down and sort of check that what I've said makes sense. Sort of given this, though, we get sort of 2 things. We get sort of 2 plus square root of 3 is a plus b square root of 3 squared. And then we also know sort of that this a and b, so a plus b squared of 3 to p plus 1 is equal to 1. But by sort of the above computation, so this computation up here, or sort of like this computation up here, we know that whenever we sort of like computing a plus b squared of 3 to the p plus 1, that's just like computing the norm. So we just get a squared minus 3b squared. That's 1 mod p. Okay, so in particular, like if I expand this out, I get, just looking at sort of first part, the part that has to give me 2, I will get the a squared plus 3b squared is equal to 2. And on the other hand, this gives me the a squared minus 3b squared is equal to 1. And so if I put that all together, I get 2 times a squared is congruent to 3 mod p. Okay. So I get sort of this has some solution. Okay, so now let me take sort of Legendre symbols. So I get sort of 2 over p times a squared over p is equal to 3 over p. But a squared over p is 1 because a squared is a square. So I get 2 over p is equal to 3 over p. But p ml is equal to 2 to the L minus 1. L is greater than 2. So this is congruent to minus 1 mod 8, which is 7 mod 8. So this 2 over p is equal to 1, just by our rule for quadratic reciprocity, or for when 2 is a square mod p. On the other hand, so by assumption, this 3 over p is equal to minus 1. And that gives us a contradiction. This is something that can't happen. Since we've got a contradiction, that means we must have assumed something that was false. So that means sort of it's not possible that 2 plus square root of 3 to the p plus 1 over 2 can be equal to 1. On the other hand, we know it's either 1 or minus 1, so it has to be minus 1. And so we're done. So we sort of established that part. So we've shown that if ML is a prime, then sort of this quantity is congruent to minus 1 mod p. So that's sort of the first part of the theorem. So we showed this quantity is congruent to minus 1 mod ml if ml is prime. Okay, so I mean, there's a little bit more involved than in Pepin's test, but he used the same sort of things. He just did some manipulations to get something that couldn't be a sort of somehow couldn't be a square. Okay, so there's sort of a different way to think about this using that we'll talk about a little bit in class on Thursday. Related to sort of exercise 2 on your worksheet. But okay, anyway, this works. Okay, so on the other hand, now we have to sort of go in the other direction. So we have to assume, sort of start by assuming that this quantity is minus 1 mod ml, and we have to show that ml is then prime. Okay, and so let me sort of just make a claim that I'll justify in a moment. So I claim that there's, in this situation, I mean, sort of for any Mersenne prime, or sorry, for any Mersenne number ml, I can always find some prime dividing it, such that 3 is not a square mod p. So if you believe this, then if I just take such a prime p, then since p divides ml, I get 2 plus square root of 3 to the 2 to the L minus 1 is congruent to minus 1 mod p. Well, that tells me the order of the element 2 plus square root of 3 is 2 to the L in sort of, in z in z square root of 3 mod L cross. So where you can think of this element as living. So it has order 2 to the L, and this is just by this lemma that we used last time. I mean, so if certainly, like if I raise this to the Lth power, I'm just squaring this, and so I get sort of minus 1 squared, which is 1. So definitely the order divides 2 to the L, but on the other hand, we saw that then to verify the exact order was 2 to the L, we just had to check that sort of when I raise it to 2 to the L minus 1th power, I got something non-zero. So this is, again, this is just using this lemma we talked about last time in Pepin's test. Okay, but then we argue just like we did in Pepin's test. So sorry, this is correct this. Sorry. So I let me think about. Great. This was right. Sorry, I just got confused for a second. So since 2 plus square root of 3 to the p plus 1 is equal to 1, so this was by our earlier example, right here. So 2 plus square root of 3 to the p plus 1 is equal to 1. And that's sort of applied, just assuming 3 was not square mod p. Sorry. Okay, let me fix this here too. I should always be working, not in, sorry, I wrote the wrong place where to be working, so we should be working now in fp square root of 3 cross. So sort of, we fixed this p that was dividing the Mersenne prime. This sort of identity still holds mod p because I folded mod the Mersenne number. So this, we already saw this identity held mod the Mersenne number. So since p divides the Mersenne number, sort of this holds mod p. Now we can sort of treat it, this as being an element of fp square root of 3 cross, and we get that its order is 2 to the L by that lemma. Sorry, apologies, I sort of explained that not so clearly. Hopefully that clarifies it. Now, this 2 plus square root of 3 to the p plus 1, this is equal to 1 by that example. And so I get 2 to the L divides p plus 1, just because sort of the order of this element is 2 to the L. And so if I can sort of raise it to any other power and get 1, then sort of 2 to the L has to divide that power. So 2 to the L minus 1 is, well, 2 to the L divides p plus 1, so 2 to the L is less than equal to p plus 1. So 2 to the L minus 1 is less than equal to p, which sort of by assumption is less than equal to ml, which is 2 to the L minus 1. So in fact, p has to be equal to ml, or 2 to the L minus 1. Okay, and so this is just like in Pepin's test. This is sort of how we, the kind of argument we made to show that sort of under this condition of Pepin's test that the Fermat number was actually prime. So same here. Okay, so I just have to justify this claim to be finished, that you can find some prime dividing the Mersenne number such that 3 is not a square modulo that prime. Okay, so first let me note that sort of, I can take this Mersenne number and I can write it as sort of some square, so n squared times a product of distinct odd primes. I mean, the point is, so I could write down the prime factorization of m sub L, and then just sort of factor out an even power of every prime to put that into a square. And then I'm just left sort of at most one, like every prime that appeared to an odd power, I'm left with just one copy of it. Okay, and then somehow I get odd primes, and sort of n and pi are not divisible by 3 either. And that's just because I already know ml is congruent to 1 mod 3, and ml is sort of not even. So sort of they're odd because they're odd, and so 2 and 3 don't appear in the prime factorization of ml. Is the point, just because I've already computed ml is non-zero mod 2 and mod 3. Okay, so good. I want to say a little bit more. So I have, so what I really can do was sort of 1 is congruent to ml mod 3. So ml is congruent to 1 mod 3. I said that, I sort of did that computation earlier in the lecture. But sort of since n squared is congruent to 1 mod 3, I sort of take any non-zero square in mod 3, I just get 1. So this sort of just goes away mod 3, and I just get the product of these other primes mod 3. So ml is just congruent to the product of these primes mod 3. On the other hand, if I look at mod 4, and by the same logic, sort of this n squared is congruent to 1 mod 4. So sort of when I look mod 4, I just get the product of these other odd primes. And then I also sort of already computed that ml is congruent to -1 mod 4, or 3 mod 4. Okay, and so if I look at this equation in particular, I can deduce the following, mean, I know each of these odd numbers, these odd primes, is going to be congruent to 1 or -1 mod 4. On the other hand, so I can sort of treat each of these being a 1 or a -1. But when I multiply them all together, I'm getting -1. So that means there's some number S of them that are congruent to -1. And sort of the number that are congruent to -1 has to be odd, because somehow I have to have an odd number of -1s over here multiplied together to get -1 on the left. There's an odd number of these primes that are congruent to -1 mod 4. Okay, so now let me sort of put that all together. So I know ML is 1 mod 3. So ML is a square mod 3. So 1 is the Legendre symbol of ML over 3. Now I can write that as the product, just using the of the PIs over 3. Just using this statement. Okay, and then to each of these, I apply quadratic reciprocity. And so since sort of the bottom thing is 3, I'm going to get a -1 every time for every PI that's odd. There's for every PI that's sort of 3 mod 4 or -1 mod 4. So I get sort of a -1 to the S. And then sort of now I get to flip all of these. And then since that S is odd, that just gives me a -1 times all of these Legendre symbols. And now, because I'm getting 1 over here and I have a negative sign over here, that means at least one of these Legendre symbols I'm multiplying together here, so each of which is +1 or -1, so at least one of these has to be -1, because otherwise, if I multiply this all together, I get -1. But I know I'm supposed to get 1. Okay, and so that's why sort of in the end, you do end up with some prime dividing ML, where 3 is not a square modulo that prime. And that's sort of the thing we used in this argument. Okay, so I'm going to stop there. I know this is sort of a messy and sort of a bit involved argument, especially sort of this part up here, to do in a lecture. So I apologize if it was a little bit difficult to follow. Hopefully some of the steps will become clearer as we continue working through exercise 2 on Thursday. So somehow the main idea to get out of this is that's what we did looked a lot like Pepin's test. We just had to work in sort of a more complicated setting to sort of arrange to get a power of 2. And all of this had to sort of do with the difference between subtracting 1 and adding 1. Okay, but we'll talk more about this in class on Thursday, and I will see you there. Thank you.